Now, one thing to note is that if a differential equation has a unique solution for a given initial condition, y of x naught equals y naught, then the graphs of the solutions cannot cross or touch at x naught, y naught. So, for instance, if you look at this direction field with a solution that goes through x naught, y naught, we cannot have another solution that crosses that. So let me redo that. So we cannot have a solution that does something like this. That is not possible. What you see here is the rectangle, basically, rectangle R, for our theorem 1, our existence and uniqueness theorem. So if the function on the right, the f of xy, is continuous and its partial derivative with respect to y is continuous, then it has a unique solution. So in our case here, in this first case, we have f of xy is negative 2y, and that's continuous everywhere. And then we have df dy equals negative 2. That's a constant function, so that's continuous everywhere. So we can draw our rectangle as large as we want, and there's a unique solution. Now, for the other differential equation, we have f of xy equals negative y over x, and problem arises when x equals 0. So problem is whenever x equals 0, then this function is not continuous. And the partial derivative has that same problem. So if you look at df dy, then the derivative is negative 1 over x, because that's a constant. If you think of y as the variable. So again, the problem is x equals 0. So if we look at the solution here, then when we draw a line, we have to exclude those problem points, right? So this is y equals, or x equals 0 as a problem point. So if we have our point x naught, y naught, we have a unique solution as long as we can draw a rectangle that avoids x equals 0. So as long as you don't start at x equals 0, you have a unique solution there. That's your rectangle R that avoids x equals 0. And again, drawing something like this is not possible. So let me, and this again is not possible. That is, if you have a unique solution. Okay, let's do one more example on the direction fields here. So the logistic equation for the population P in thousands at at time t of a certain species is given by dp dt equals p times 2 minus p. If the initial population is 3,000, that is p of 0 equals 3, what can you say about the limiting population limit of p of t as t goes to infinity? So I'll import the drawing in a moment, but let's kind of look at what is happening. So if we start at p0 equals 3, we have a slope that is negative for the direction field, and so we're going down. But the further to the right we come, the less steep our direction markers become until they flatten out. So we start at 3, we go down, but we're not able to cross that line y equals 2 or p equals 2. So the limit of p as t goes to infinity, that equals 2, or 2,000 in terms of the species. So that is the limiting population. So now let's take a look at a population of 1,000. So that means that p of t is 1, right? 1,000. Can it decline to 500? Well, if we start at t is 0, we have direction markers that are positive, and so our population will increase and then kind of level off to, again, that population of p equals 2 or 2,000. Now that's if we start at time t is 0. If we start at time t is 1, we would start, let's say, over here, and we slowly increase, and then go to p equals 2 again. So we wouldn't be able to go down towards 500 or 0.5 because the direction markers don't allow us to. So the short answer is no. And can a population of 1,000 ever increase to 3,000? Well, again, if we start at 1, no matter where you start, at some point your direction markers are forcing you to level off, and we cannot cross that horizontal line here. So let me import the picture here. And then I'll show you. Let's resize that. So what I've done here is I've also drawn this horizontal line, and that horizontal line corresponds to the solution p equals 2. Right, so this one right here is p equals 2. And let's double check that when you plug in p equals 2, p of t equals 2. So let me point out that this is the solution that is identical equal to 2 no matter what t is. If you plug that in, the constant solution, you get 2 times 2 minus 2, that's 0, and the derivative of a constant is 0. So we have 0 equals 0, so the constant solution is a solution to this differential equation. And can a population of 1,000 ever increase to 3,000? That would mean that our differential equation would have to cross that solution p of t equals 2. Now, our function here, and think of that p as your y value, the function f of x comma y, or in this case f of, let's write that down. So instead of f of x comma y, we have f of t comma p. That is, let's write that out, 2p minus p squared. And then if we take df dp, right, instead of df dy, that's 2 minus 2p. These functions are both continuous on the entire TP plane, or the XY plane, and so there's a unique solution. So the short answer here is no, because what you would get is that one of these lines to go from 1 to 3 would have to cross this solution, which is a unique solution, and that cannot happen.